Hi folks, here we have a question all about negative charge carriers travelling in a counterclockwise direction in a circular coil, and we've got a uniform field. We want to know the effect of the magnetic force on the coil. So as ever, press pause, try the question, and then press play for the answer. Okay, so we have these negative charge carriers. Now, I think obviously when we look at these kind of questions, we're always tempted to talk about Fleming's left-hand rule. Now, I would say in this case, you just need to pay a bit of attention here to the fact that we're looking here at negative charge carriers. Now, negative charge carriers do the opposite of positive charge carriers. Why is that important? Well, because when we use Fleming's left-hand rule, which is what I'm going to use here, we always assume we're dealing with positive charge carriers. So I'm going to assume that instead of we've got negative charge carriers going counterclockwise, we've got positive charge carriers going clockwise. It's a little mind shift that you make, but it's basically a double negative, right? We've got negative things moving in the opposite direction to our positives, which are moving clockwise. So I'm going to put, for example, some arrows here. Okay, at the top of this circle, the positive charge carrier is going to be moving to the right. At the bottom, it's going to be moving to the left. Okay, these are the sort of tangential velocities that you're going to have in this case. I'm then going to use my left-hand rule. So right now, I'm afraid you cannot see me doing so. I wish you could. Okay, is I'm going to be pointing my first finger towards the screen. I'm literally doing this right now. I'm then allowing my second finger to point to the right, and I've got my thumb, which is currently pointing upwards. If I then take that hand and rotate everything around my first finger, so keeping my first finger pointing to the screen and now pointing my second finger to the left, I've got my thumb pointing down. So hopefully you can see there we've got a force on the top and the force on the bottom in opposite directions. Makes sense because we've changed the direction of the current. Now what will that do? Well, we've got a force pulling our circle in opposite directions, and so the result of this will be that the diameter of the coil is going to increase. Okay, and that is our possible answer here. Now I'm just looking at the other answer to see if we could rule any out. We're always keen to make sure we rule these things out. We've got these ones here about rotating in the plane of the paper. These are not possible because as soon as you see our field into the plane or out of the plane, the force cannot be in those directions. Okay, when you're dealing with Fleming's left-hand rule, you have 6 possible directions, 3 dimensions with a positive and a negative in each dimension. As soon as you see the field in this case, the Z dimension, you know that the force is going to have to come in either the X and the Y. The force cannot be in the same direction as the field itself. Okay, so that's just a little trick there that can allow you to rule out a couple of answers. So really at the beginning, we could have got rid of A and B fairly simply.